Hey, welcome to another session of the Flipped Classroom for Calculus, session 33. Today we're going to talk about mean value theorem and fundamental theorem of calculus. It happens to be a snow day, so what a better way to spend a snow day than talking about calculus. Mean value theorem, the easiest way to talk about that is perhaps by drawing a graph. Here we've got a graph, we've got some function, f of x, and I have three rectangles drawn here. Okay, the first rectangle, which is this small little guy here with the dots on it, I've started it at A and gone to B, so it has a width of A minus B, or B minus A, and has a height of f of A. So that area under the curve, if we use this to measure the area under the curve, it would be quite an underestimate. Okay? Now the next rectangle, I chose my value of f of b, and that's the height here at b. Again, the width of this rectangle would be b minus a, and as you can see, this large rectangle, the blue rectangle here that I'm outlining, is way too big an estimate of the area under the curve. Okay, so what the mean value theorem says is that there has to be one perfect rectangle, if you want to think of it that way, in between these rectangles that is the exact area under the curve, and the function value at that of that rectangle, where we take it on the curve, the height of that rectangle will be the average value of the function. So here that's indicated by C and f of C. And as you can see, excuse me, by the dashed line, this rectangle, even though it's too big here and too little here, those areas cancel out, is a good approximation of the area under the curve. Okay? So how do we calculate the mean value theorem? Well, we've actually done this in the last section when we calculated average values of functions. It's basically the same thing. So you've done a number of problems. So remember, it's 1 over b minus a times the integral from a to b of f of x. Okay? Up till now, the only way you've been able to find that integral really is using geometric shapes or finite sums. The fundamental theorem of calculus really has two parts. The first part is, it seems simple, but it's really a very powerful theorem. Let's say that f of t is an integrable function, and we write this integral as and the integral of f of t from a fixed point on the interval, to x, which can be any point in the interval ab. Okay? We can define the area under the curve from a fixed number a to x as the antiderivative of x. That's what that capital F stands for. And therefore, the antiderivative of x would simply be equal to the integral of f of t from a to x dt. Okay, actually, this should be a dt here. That's a typo. As long as f is a continuous function, the antiderivative of x will have a derivative, meaning it's differentiable, at every point x in the closed interval ab. And the derivative of f of x dx is equal to the derivative of this integral from a to x of f of t. And that will equal f of x. So what are we saying? What we're saying is if we take the derivative of an antiderivative, we're back to the original function. It's kind of like taking your socks off, putting your socks back on, and taking your socks off again. Okay? This is the first part of the fundamental theorem. In class, I will give you a geometric interpretation of this theorem, which may be more intuitive. Here's a sample problem. Let's say we want to find the derivative of the cosine of t with respect to t, but we want to find that derivative with respect to x, the dx. And our a and b are negative pi and x. According to the fundamental theorem of calculus, this derivative will just be the cosine of x. You just take the f of t and substitute x into it, and it'll be cosine of x. How do you use the fundamental theorem if you have a composite function? Well, we have to bring out our old friend called the chain rule, okay? So here's a sample. Let's find dy dx if y equals the integral from 1 to x squared. Notice that this is a composite because it's no longer x, it's x squared, of the cosine of t dt. Y is a composite, okay, and we have to use chain rule. Let's let u equal x squared, and let's let du dx be 2x. Okay, so here we go. dy dx, I just retyped this. This is the problem. F of t would be cosine of t here. If we let u equal x squared, du dx is 2x. Remember, chain rule, one way to express chain rule, derivative dy dx equals the derivative of the outside function times the derivative of the inside function. Y of u in this case would be the integral from 1 to u of the cosine of t dt, and dy du by fundamental theorem of calculus would be the cosine of u. So dy dx equals dy du, which is the cosine of u, times du dx, which is 2x. Back substitute what u is, you get the cosine of x squared times 2x. Not too bad. Here's another problem. Find a function y with equals f of x with a derivative dy dx equals tan x that satisfies the expression f of 3 equals 5. Okay? Alright, so here what they're asking you, they're giving you the derivative and they want you to find the function that has this derivative of tan x. Okay, we can use the fundamental theorem of calculus for this. Alright, notice we can write an integral of the tangent of t according to this fundamental theorem of calculus. If we say y equals the tan of t from 3 to x, then the derivative of that will be tangent of x. And that's what I want, dy dx, to be tangent of x. So I know the function has to be something like the integral of tangent of t, but how do we deal with this value f of 3 equals 5? Well, notice, if we evaluate this integral at x equals 3, in other words, the top limit here is 3, and the bottom limit is 3, remember what the value of any integral taken from 3 to 3 or a to a, it's going to be 0. Okay? So therefore, the original function must be y equals y equals f of x, which equals the integral from 3 to x of tan t dt plus 5. Why is that? Because I know that f of 3 equals 5, and the only way f of 3 can equal 5 is if I add 5 to the original integral, because evaluating just this integral from 3 to 3 is 0, so therefore f of 3 has to equal 5. We can check this by taking the derivative using fundamental theorem. dy dx would be tan x, and the derivative of 5 would be 0, so therefore I'm left with tan x, and that's what we were originally given. Part 2 of the fundamental theorem. Okay, this is sort of a more practical applied part of the function. It says if f is a continuous function on AB, antiderivative of x is an antiderivative of x, then the integral from a to b, f of x, can be evaluated by taking the antiderivative at b minus the antiderivative at a. I will prove this theorem in class. Here's an example problem. Evaluate the integral from negative 1 to 3 of x cubed plus 1 dx. Step 1, take antiderivative. That equals x to the 4th over 4 plus x. Evaluate at 3 and negative 1. So when I do that, f of b, capital F of b, minus capital F of a is 81/4 plus 3 minus, okay, there's a minus sign right here, 1/4 minus 1. And this comes out to be 24. What's next? In the next video, I will show you some applications of antiderivatives. Right now, let's work on problems 1 through 32 on pages 383 to 384. Peace.